So today our agenda would be to discuss the debiasing algorithm and to see the main results that they obtained due to the debiasing. So that would be our agenda today. Okay, so before um, like discussing the mathematical formulation of the algorithm, let us try to like pictorially understand, because this is all about vectors and vector spaces. Let us try to pictorially understand what is going on. Okay, so let us draw. So this is the gender neutrality axis. Okay, from gender specific, it runs up to gender neutral. So this is like the more you are on the lower quadrant, the higher is the word, like the higher are the chances that the word is gender specific, and as you go above, the word becomes more and more gender neutral. On the other side is the she he axis, which is the gender bias direction. Okay, here again let us draw the same thing. It will be clear in a moment like why I am drawing this. So if you recall, one of the steps of the algorithm, the first step of the algorithm was to neutralize. Okay? After you have computed the gender subspace, the first step was to neutralize. Now, what does this step neutralize mean? So for instance, say you have two words, nurse, which is located here, and you have doctor, which is located here. Okay, so say this is your situation. So this is a biased situation, right? Because what you see here is that nurse is more close to she, whereas the doctor is more close to he. So this should not be the case. This should not be the ideal case, because these are actually gender neutral occupations. However, due to stereotypical issues, they fall in the uh, in the quadrants according to what you see here, like one close to she and the other close to he. Now, post neutralization, what would you expect the 2 points to be? Or where would you expect the 2 points to be post neutralization? So you want to neutralize this bias effect, okay? And you want, like, these two should no longer have any stereotypicality in it. Okay, they should become gender neutral. So where should these points lie after neutralization?
On the y-axis.
On the y-axis. Very good. And in this quadrant, right? So basically, now
Yes.
after neutralization, so what have you done in the neutralization step? You have tried to push these 2 points on this gender neutral axis, and now nurse and doctor, both of them lie on the gender neutral axis. Okay, so that is the neutralization step. Now the other step was, let's again draw, and then we will talk about the other step. Now say there are two gender specific words. Okay, so this is the equalize step. Suppose there are two gender specific words okay, and there is a gender neutral word. After neutralization, the gender neutral word has come on the gender neutral axis. Okay, so this has happened. Now you have these two words which are gender specific, and they are well placed in their own quadrants, correctly placed in their own quadrants. But then there is an issue. What is the issue? What is the issue? You should be able to see this, right? I have already drawn it. What is the issue? These two are well placed in their own quadrants. Nanny has been neutralized, but still there is some problem. I mean, the picture should be able to tell you what is the problem.
Male is more gender specific than female.
No,
Sir,
it, huh?
Nani is more closer to female than Nani.
Very good, very good. That's the point. So these two are not equidistant. Ideally, they should be equidistant. Okay, so this is shorter and this is longer. So the equalize step actually tries to resolve this. So post equalization, they become equidistant. Okay, so these are the two important steps that need to be like executed one after the other in order to do the complete debiasing. Okay, so now we will, once we have like pictorially understood what is what, like now it would be easy for us to follow the mathematical formulation for the algorithm. So as I said, the first step is the gender subspace construction. So we had already discussed this a little bit when we were talking about the direct and indirect bias quantification. Okay, so here we will more formally state it. So let's say W is the set of all words. The notations remain very similar as earlier. Let's say this is a new notation. DI is the gender defining defining set. Okay, mu I is the mean of each defining set, and let's call B as the bias subspace. Okay, also the embeddings are from the real space RD for every W in capital W. Okay, and the gender defining sets so if you recall in our empirical experiments when we were doing this analysis of direct and indirect bias, we took 10 such gender defining pairs based on their accuracy of classification. So if you recall, these were like she, he, then male, female, I guess Mary, John, etc. So there were such 10 such pairs. So these are the gender defining sets. Mu I, as I have already defined, so it is the mean of the vectors. In a particular defining set. Di. Okay. Now we will do all calculations with vectors, okay, shifted to the origin. Okay, in order to do this, what do we need to do? If you try to brush up a little bit your old statistics days, this actually amounts to giving every vector a mean shift. Okay. Now I will define something and you will tell me what is this. What is this? If you think of it carefully, these are two vectors and this is kind of like you can rewrite it as V transpose V. Okay. If you consider W minus mu I is a vector V, then you can write it. So this is rough work. Then you can write it as V transpose V. What is V transpose V? What is V transpose V?
And mod V whole square.
A little more thought. V transpose V, what does it do? What does it compute?
Magnitude
This
of the vector,
is it.
square of the magnitude. I mean.
There is a I equals 1 to n, and then there is a W belonging to di. So this C is this, what is this? This is a vector. This final C, this is a vector. Think carefully. This is simple mathematics. There is no trick, no jugglery here. Think carefully. What is this C? What type of mathematical object is C?
Is it the variance like?
Very good. So this is a variance. I mean, variance what? What is the mathematical object? Is this a vector?
No, it's a scalar.
It's a scalar.
Uh, uh, like
Sure.
uh,
Compute each of the terms. Think that this, okay, let me give you some more hints. Recall that W vector is a 300 dimensional vector. So go by first principles.
is it the covariance matrix? Like
Very good. Yes. Why are you asking me? You should be confident. W is 300 sorry, W transpose is 300 cross 1 and W is 1 cross 300. Okay, I mean with the mean shift, whatever. So therefore, the thing that is finally obtained is a 300 cross 300 matrix. And the nature of the matrix, this V transpose V, is nothing but the covariance matrix. Now, why are we suddenly interested in this covariance matrix? Okay, before that, I give you the answer. Like, why did we compute this C? So from this C, we will execute a singular value decomposition of C. Okay, and the first K rows defines my bias subspace B. If K is equal to 1, then B is equal to G that we had read earlier. Okay, the gender direction. This is the gender subspace. And this is gender subspace when K is greater than equal to 1. And when K is exactly 1, this is the gender direction. Okay. This is the gender subspace. Typically, you take K equals 3 or 4. This defines your gender subspace. But you have already seen that while quantifying the direct and the indirect biases, we have assumed K equals 1, which actually reduced B to G or the gender direction. So when K is equal to 1, it's a single direction, which is also called the gender direction. Now, why is this SVDC a good representation, or like why did we in the first place compute the covariance matrix, and why did we say that this SVD of C is a good representation of the gender subspace? Why? See, I have explained to you through pictures. You should now try to imagine things through pictures. This is nothing simple vector algebra. And some of the things that I have taught you in the last class. Do you remember the principal component study that I was showing you?
Sir, is it the dimension? Is it related to dimensionality reduction?
Of course, SVD is doing dimensionality reduction, but why the covariance matrix? Why suddenly the covariance matrix? Covariance matrix of what? What is this covariance matrix of? First of all, this covariance matrix is a matrix constructed from the gender defining sets. Recall. So you have to, at every step, you have to recall what is happening in the previous step. Otherwise, it will be difficult for you to explain stuffs. So if you recall, this is a covariance matrix of the gender defining pairs. You have the representation of the gender defining pairs. Now, if you think of that original empirical evidence that I was trying to put forward in one of the previous classes, I told you that these are the PCA components. And do you remember what was this axis?
Sir, variance explained.
Variance explained.
Yes.
So now do you make 2 plus 2? Why we are computing the covariance matrix? Because we want to find out what are the important directions that can explain the variance to the maximum. Okay, so we want to capture through B, we wish to capture those vector directions that explains max variance. And our assumption is that the first 3 or 4 such directions should be able to explain like almost 90 to 95% of the variance. So that's why we have used the covariance matrix and have done an SVD of the covariance matrix to compute the bias space. So now we have the bias space ready, okay, or the gender subspace ready. So B is now my gender subspace. Now neutralization was my step 2A. So this was step 1. I guess I have numbered it, yes. And this is step 2A, where we try to do neutralization. Now this is a simple step. So if you recall, your N was the set of stereotypical words. Typical words that should be ideally gender neutral. Okay. So for instance, nurse and doctor. This should be ideally gender neutral. So what we do for every word in N, we re-embed W like this. And what is WB? Any guesses? Come on, no guess. This was already like talked about when we were discussing the empirical observations of direct and indirect bias. What is WB? What is this? Huh? What is this? Oh my God. What was this? What was this? We said, right? W is equal to W norm plus WG. And this WG was defined like this. What is WG?
Sir, component of W
The
along the
projection.
yes.
Projection of W on the gender direction. Similarly here, projection of W on the gender subspace. Okay, so that is WB. So you just take every word, remove the gender part, gender component, okay, and that becomes your new W. Fine. So now nurse, doctor, etc. get rid of their gender components. Okay, and they come on the gender neutral axis. Fine. So this is what you do to remove the gender stereotypical words to make them gender neutral. Now the equalize step. This is a bit more tricky. Okay, so the equalize step actually works on the set of equalities or equality sets. Let's call them E. These are set of all equality sets. Okay, and E belongs to capital epsilon. So these sets are like gal, guy, grandfather, grandmother, etc. So these are all equality sets. Okay, like the example that I had showed you earlier. Here again, we will compute mu, but this mu is on the equality sets now. Okay, this mu is on the equality sets. And we also define something called the nu, which is mu minus mu b. What is this? What is this? Any guess? Any guess? No guesses. What is mu b? What is your best guess about mu b?
projection of mu in the bias direction.
Projection of mu in the gender subspace. So nu is the mu part with the gender part removed from it. Okay, nu is that part of the mean from which the gender component has been removed. Now for every W in E, you can write W to be equal to, as I had showed you earlier, the normal part, W normal, and the gendered part. Okay. So for each of the W's in the equality set, you equate this W perpendicular or this W normal to the average of the embeddings, average of the embeddings of the words in E, okay, outside B. So this means what? What am I referring to? Just now we have defined. I am equating this part, this W normal, for all of the W's in the equality set to that part of the mean which is outside the gender subspace, or which is free of the gender component. This is the other way to tell it. Okay, outside the gender subspace or free of the gender component. So what is this?
Nu.
Very good. So this is new. So now we have W is equal to nu plus WB. Again, here we want to work with reference to the, in the bias subspace, we want to move everything, or in the gender subspace, we want to move everything to origin. Okay, we want to shift everything to the origin. So therefore, this WB is shifted to the origin. So see, we are wanting to construct the new W. In order to do this, we are doing all this drama. So we want to shift this WB to the origin. Okay. So again, we give a mean shift. So within the bias subspace, what is the mean? Or within the gender subspace, what is the mean? Mean.
Mu B.
Yes. Within the gender subspace is mu B. So I want to replace this WB with so now I have Okay. Now, so far, so good. But whenever I am constructing this new W, I also want my original properties of W to hold. So what was my original property of W? For every W, I wanted it to be. So in what space was I working? Any vector or unit vectors? All our constructions, all our assumptions was around unit vectors, right? So we wanted everything to be all the new W's that are created, wherever it is. We wanted them to have a unit vector representation, right? So here also, we want the new equalized W's to be unit vectors. So therefore, I have this constraint that I would need the norm square of W to be 1. So this means that I want so if I expand this, what will I get? Typically do not put brackets. The norm sign is enough. So when I square this, what should I get? What is A plus B square? How much is this? Let me tell you. This is or if we remove this dot, then this is, if we express this as a product, cos theta, because that's the dot product. So now here, so what is the angle between nu and WB minus mu B? What is theta? Nu is the perpendicular to the perpendicular part of the, nu is the perpendicular part of the mean, and WB minus mu B is in the bias subspace or the gender subspace. So what is the angle between these two?
90.
90 degree. So cos theta is 0. Okay? So this part vanishes. So therefore, we want mu square plus WB minus mu B square should be equal to 1. So we want that WB minus mu B should be equal to 1 minus mu square root. Okay. Now why all this drama? Now you will ask me why all this drama. Okay. So now I want to express W equal to nu plus, if you recall, WB minus mu B. Okay. But I do not have access to this. Because in the gender subspace, everything has got normalized. Okay. I do not have access to this, and in the gender subspace, everything has got normalized. So everything is in the form of a unit vector, right? So what do I have access to? I have access to this. Okay. This as a whole. I do not know this part separately. Okay. Then I could have like easily multiplied and got it. So I do not know this part separately. So this whole thing comes as a quantity, say A. Okay. This whole thing comes as a quantity, say A. Now how do I recover WB minus mu B from A? What will give me WB minus mu B from this whole quantity A? If I multiply A with this, then I will get WB minus mu B. But as I said, unfortunately, I do not have access to this. Is there any alternative? Is there any alternative trick that I can use? So in order to maintain this, what have I just now obtained? What was the constraint that I just now obtained? Just now we obtained that if this constraint has to be satisfied, then WB minus mu B should be equal to what? Just now we obtained, right? This should be equal to 1 minus mu square. Now, since I do not have access to this, I will use this as the scale. Okay, so I can obtain this WB minus mu B by multiplying A with this, because this is nothing but WB minus mu B. So although I do not have access directly to this quantity, I can compute 1 minus norm of nu square root and multiply that with A that I am obtaining. This I have access to. So I have access to only the normalized vector. I do not have access to what it is getting normalized with, and I do not have access to the original vector. So I only have access to this normalized vector. So the way to recover the original vector from the normalized vector, I can multiply it with 1 minus norm of nu square root, because I have proved that in order to maintain W square or the norm of W square to be 1, I need this constraint to be satisfied. So therefore, instead of this W minus mu B, I can use square root of 1 minus mu square. So therefore, now I can write W is equal to nu, which I have access to, A, which also I have access to from the gender subspace, and 1 minus mu square, which also I have access to. So this is my new equalized vector. So for each W in E, okay, we have W equals so now with this we have neutralized as well as equalized the space, the vector space, and the individual vectors. Like we have neutralized all the stereotypical vectors and we have equalized all the vectors that belong to equality sets. Okay, we still could not complete. So tomorrow we will finish like the small set of results that they had obtained after debiasing, and we will see like how this has reduced the bias, and then we will start the next segment of our syllabus, which is on content governance. So we'll stop here. Any questions? Yeah, today it was a bit mathematically involved, but I think like if you follow the whole like derivation, it's not so complex also. Any questions? Okay, we can stop here.